So we get for every natural number, we get another statement, right? So this is a sequence of statements involving natural numbers. Of course, we want induction. We don't even need strong induction. Regular induction's fine. Okay, so for each natural number, let P of n be the statement. A plus b to the n is the sum from r equals 0 to n of n choose r, a to the n minus r, b to the r. So our base case is going to be P of 1. Okay, so that's the statement we get by plugging 1 in. Again, that's going in for n. So the sum goes from 0 to 1, right? Because n for all the n's goes 1. Okay, and we're just going to need to expand that out. So let's see here. Let's see if I have enough room here. So plugging 0 in for r, I get 1 choose 0 times a, right? Because if 0 goes in here, that's 1. And now I want to choose, or I'm sorry, now I want to plug 1 in for r. So it's 1 choose 1. Well, if 1's going in for r, that's going to vanish because that's going to be 1. So that's just going to be b to the 1. Okay. If you compute on the side, 1 choose 0 is 1. Right, we said anything choose 0 is 1. So it gives me a. And 1 choose 1 is also 1. N choose n, in fact, is 1. And that's true. Okay, so the inductive step. So let n equals k be arbitrarily chosen. Assume that p of k is true. Remember what that means? We're assuming that this at k is true. We want to show that p of k plus 1 is true. I think I'm going to grab another piece of paper. This is going to be a bit of writing. Okay, so here, let's start with this, right, where we can use our inductive hypothesis right off the bat. So you've got a plus b to the k is the sum from r equals 0 to k of k choose r, a to the k minus r, b to the r. And I'm going to expand that out next. So I'm going to choose a lot of terms so you can see the pattern when we get there. So now I'm actually just going to write this out, showing a lot of terms. Okay, so we start by plugging in 0 for r. Okay, if I plug 0 in for r, that's a to the k. Now we plug 1 in for r. Notice also that the sum of the exponents is always k. That's helpful for keeping track of everything. Now I plug 2 in for R. Okay, I'm going to plug 3 in. Got to plug 4 in. And then I'm going to say plus dot, dot, dot. And then the term before the last, right? The term before the last, we're going to be plugging in k minus 1 in for R. So the term before the last, right? If the last is k, the one before that is k minus 1. So k minus 1 in for R. And then the very last is when I plug k in for R. Again, if I plug k in for R, I get k choose k. Well, k minus k is 0, a to the 0 is 1, b to the k. Okay, so the next thing I want to do is build a bridge. I want to get to p of k plus 1. Well, I don't have k plus 1 on the left, so let's multiply the left side and the right side by a plus b. Okay, so if I multiply the left by a plus b, I get, let's see here, a plus b to the k plus 1. So yeah, multiplying that by a plus b. Now the right side, there's several terms. So if I multiply the right side by a plus b, that would be distributive property. Every term gets hit by a plus b. Okay. So this gets hit by a plus b, this, etc. Okay, so we keep going, remembering a plus b for each term. Okay, and then finally this term gets hit by a plus b in this term. So the hardest part is probably for students just keeping track of all of the objects and being careful. Okay. Okay, so now we're going to distribute. Okay, so this is equal to, okay, so if I multiply this by a, notice the exponent on a goes up. That's actually really good for building our bridge. So we're happy about that. And then we multiply here. Okay, so that was just distributive property, distributive property. Okay, let's do some more. Let's now distribute this. So let's see here. What is that? That's k choose 1, a to the k when you add exponents times b, plus k choose 1, a to the k minus 1, b squared. Okay, so I'm just going to distribute this over the first, but you realize we keep distributing all the way down, right? So here I would have k choose 2, a to the k minus 2, oops, hang on just a second. A to the k minus 1. We add exponents, right? So yeah, a to the k minus 1. Okay. B squared, that looks good. And then you keep going until eventually you've got k, choose k minus 1, a b to the k, plus k choose k, a b to the k, and finally k choose k, b to the k plus 1. So I didn't show all this distributing. I actually just showed enough so you can see the pattern I'm going to use. But if you want to show more, that's perfectly fine. And so exactly at this point, I want to look for maybe terms where I can do some factoring. Like, do you notice that this has an a to the kb, and so does this? It'd probably be smart to group these together and then factor. I mean, same idea here, right? A to the k minus 1b squared, a to the k minus 1b squared. These go together. Okay, so let's go ahead and factor. But notice what happens when you factor, right? If I factor this out, we get that property we talked about before. Remember k choose 0 plus k choose 1? That's k plus 1 choose 1. Remember that? We talked about that a little while ago. Okay, so if I factor this out, I've got this plus this, which is k plus 1 choose 1. So that's really why we talked about that property before. So where was that in the notes? Right here. Okay, so we're going to use that over and over and over again. So if I look here, right, imagine factoring this out. If I factor this out, you're left with this plus this. Well, k choose 1 plus k choose 2 should be k plus 1 choose 2. And what do we factor out? A to the k minus 1 b squared. Okay, so dot, 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 we keep going. And then here, well, these actually match. So I'm gonna keep that. Oh, I don't want to keep, okay. Yeah, so that does, I mean, that factorization is not so good. Let's group these. Yeah, that doesn't even make sense. It's these who I want to group together. Excuse me. There we go. Okay, and those are one off. So that should be k plus 1 choose k. There we go. K plus 1 choose k. A, b to the k. And then I've got that final term of k choose k, b to the k plus 1. So it mostly looks good, right? Mostly. But this seems problematic, and so does this. But with a little care and thought, it's actually not. Because we said earlier that anything choose 0 is 1. So it doesn't matter how I represent this. It could be k choose 0, 7 choose 0, 100 choose 0. Those are all the same number. They're all 1. So I can call this k plus 1 choose 0 because it's equal to 1, right? So it's the same number. You're just writing it differently. And here we said anything choose itself is also 1. So if I wanted to, I could replace this with 5 choose 5, a million choose a million. They're all different representations for the same number, 1. So I can call this k plus 1 choose k plus 1 because it's also equal to 1. And if they're both equal to 1, they're equal to each other. So now I just want to write this in summation. So let's see here. R is going from 0 to k plus 1. For the a's, we have a to the k plus 1 minus r. And if you check this, if I plug 0 in, I do get this. If I plug 1 in, I do get this, right? And then b to the r. And that's what we wanted to prove. So since k was arbitrarily chosen, it follows by mathematical induction that a plus b to the n is equal to the sum from r equals 0 to n of n choose r, a to the n minus r, b to the r for all, don't forget to quantify, natural numbers n. And that's the proof for the binomial theorem.